methods of charging. And we are going to see the different classification of the AC and DC chargers and the protocols used, etc. Sorry, something happened. Please hold on till I load the slide again.
Yes, sir. Yes, sir.
Can you see the slide?
Yes, sir. Yes, sir. It is available.
Yeah. Okay. Okay. See, there are various nomenclatures being used for EV charging stations. Something like it is called as electric vehicle charging station, or EV charging station, electronic charging station, and for EV charger, it is either called as charging point or charge point. The more technical term is electric vehicle supply equipment. It's called EVSE often. And there are AC chargers, slow chargers, fast chargers, quick chargers, rapid chargers, etc. Let us see one by one. What is that? This, see, fast charger, quick charger, rapid charger, all mostly indicates DC charging system, which are generally faster, much faster than AC chargers. See, broadly, it is classified as AC chargers and DC fast chargers. You know what is AC? What is the difference between AC chargers and DC fast chargers? AC chargers are equipments, maybe a protection equipment, measuring equipment that extends the AC power to the onboard charger of the vehicle. So it doesn't consist of a charging equipment. Basically, AC charger is nothing but an equipment which extends the mains power to the onboard charger of the vehicle through some protection devices. And commercial chargers, they use metering as well as they may have IoT for payment and authentication, etc. DC fast chargers, they are the real chargers. So the fast chargers, normally they are DC fast chargers are off-board chargers. They are kept outside the vehicle, and these fast chargers are have a very high current rating and a very high power rating, and this can charge the vehicle in almost hour's time. See, there are, as I told you, the chargers are classified by different different methods are used for classifying the charges. So one is mode based on the modes of charging. The mode 1 chargers are generally standard domestic outlet with proper earthing and circuit breaker and earth leakage protection. This is what normally each and every house, every home will have this facility to charge their electric vehicle. This is nothing but a standard outlet with a circuit breaker, with a for overcurrent protection and earth leakage protection. Normally, this is called residual current circuit breaker (RCCB) or earth leakage circuit breaker. So either RCCB or earth leakage circuit breaker is being used to avoid electric shock to the personal using it. Mode 2. This has got a charge protection device. The charge protection device is nothing but equipment which protects the onboard charger from external factors like over voltage, under voltage from the mains, or overcurrent from the vehicle, then electric shock to the user. It has got either RCCB or earth leakage protection device to protect from electric shock, and even sometimes mains reversal like phase neutral reversal. All those things they detects and protects the charger from an external faulty condition. Mode 3 chargers. Mode 3 chargers from a wall-mounted AC charger. See, wall-mounted AC chargers. Normally wall-mounted AC chargers are being used commercially. You can find out in parking lots or in theater or malls where the energy is measured. See, there will be an energy meter that measures the energy, and these are all become commercial chargers. It measures the energy, requires authentication, needs payment after charging. So all these facilities will be included in mode 3 charging. And mode 4, DC fast charging. DC fast charging, as I told you, this is the real charger. It has got complete charging circuit and all. And there are many varieties of DC fast chargers. Internationally, 3 protocols are being followed. India, there is a separate protocol is being followed. And those things we will see in the upcoming slides. And one classification we saw is mode, based on the mode of charging. And the other classification is based on the level of charging. See, level 1 chargers are generally from a 120 volt or 110 volt supply, usually used in US, in the United States, where they have outlet of 110 volts. And the maximum current limit for these chargers are 15 amps. So the power is limited by the maximum current available. So 1.92 kilowatt is the maximum power it can deliver, that can provide maximum of 7.5 kilometers per hour charging. If you charge it for 1 hour, you can travel for 7.5 kilometers. So even if you charge it for 10 hours, you will get 75 kilometers range. And this level 1 or level 2 chargers are used at home. Level 2 charger. Level 2 is a level 2 EVSE, that is electric vehicle supply equipment. It operates from 220 volts system used in British or Indian standards, where we use 220 volt outlet. And here the maximum current available is, see, generally at home we don't get a current more than 15 amps, except like we have a special socket where you can have a current of 30 amps maximum. So the power is limited to say about say somewhere around 3.5 kilowatt for 15 amp socket, and some 7 kilowatt for 30 amp socket. So when used commercially, you can go up to 80 amps and it can provide up to 19.2 kilowatt of power, which provides a 100 kilometer per hour range. So this 100 kilometer, and when you recover so high range for per hour charging, the onboard charger should be capable of providing that current. I have told you these chargers are all AC chargers. Level 1 are different modes of charging what we have seen, except for DC charger, mode 1 to mode 3, and level 1 to level 2. These are all AC chargers, and they depend upon the onboard chargers for charging. So even if your mains is capable of providing 19.2 kilowatt, the charger should be capable of charging at that power value. So only when that is possible, you can utilize so much of current from the mains. And see, there are AC in AC also. There is AC fast charging also is available, where high-end vehicles like Benz or BMW, they use AC fast charger. Tesla and all, they use AC fast chargers, where their onboard charger has very high capacity and it can charge the vehicle at a very fast rate. Maybe 2 to 3 hours it can provide a full charge. So it can provide up to 19.2 kilowatt and 100 kilometers range per hour charging. Level 3 is off-board DC fast charger. Again, this is what we have seen in mode 4. That mode 4 charger is nothing but level 3 charger, and off-board chargers, they start from Indian chargers start from 15 kilowatt, and the chargers can go up to 350 kilowatt or even more nowadays. So it can provide 100 kilometers to 450 kilometers per hour charge. See, based on charging plugs, the chargers are classified differently. See, like on the right hand side, you can see a blue plug. This is nothing but an industrial socket used by industry. Maybe even this type of sockets are used in our air conditioners also. When this type of plugs are used, this plug falls under AEC 60309 2 standard. And when this plug is used for charging, for AC charging, this is called type 1 charger. And you can see a black color charger on the bottom. That black color charger, black or brown color charger, ash color charger, this charger is called type 2 charger. They are called type 2 chargers. And you can see different pins, like you can have 3-phase supply, L1, L2, L3. Whereas on the type 1 charger, it is purely for single phase operation. Whereas type 2 charger, you can either use single phase or 3-phase. So you can see 3 lines, L1, L2, L3 and neutral. Either when you use single phase, use L1 and neutral. When you use 3-phase, all line 1 to line 3 and neutral. And in addition to that, there are 2 more control pins, 2 more sensing pins. One is called control pilot, CP pin, and another one is proximity pilot. The last one is power earth. It's earth wire used for safety purposes. This control pilot, we'll be seeing how this control pilot works or proximity pilot works in the upcoming slides. See, this control pilot can be used for communication between vehicle and the charger. Like whether the charger is connected to the vehicle or plugged into the vehicle or removed from the vehicle, or what is the maximum amount of current available from the mains to the onboard charger, or similarly PP pin also provides information about the connectivity. Type 3. Type 3 is single and three-phase vehicle coupler with safety shutters. When it has a safety shutter, it is called type 3 charger. Type 4 is again DC fast charger. Let's start again. Please hold on. Again, I'll share the screen.
Yes, sir.
See, this again, this type 1 charger. So, what are the facilities the type 1 chargers has got? That we will see here. Can we, is it possible to remove this one? Okay. Normally, this type 1 charger or type 2 chargers, they have earth leakage protection called RCD, residual current detection. Earth missing protection. See, this is one of the main protection which is the requirement for the top, first two protection what I told, they are the main protection which is required by the standard. So any charger, whether type 1 or type 2 charger, you should have, or even DC fast charger, should have earth leakage protection sensing, earth missing protection also. So safety is the very high important criteria in charging application. The safety to the personnel who is using is given more preference. Then it also provides overload and short circuit protection, input voltage protection against input over voltage or even under voltage protection also can be given. This uses the industrial circuit plug as shown here. Then type 2 charger. The type 2 charger also, so in the same way, what type 1 charger is using, this also uses earth leakage protection, earth missing protection, overload short circuit protection, input voltage protection, and this is capable of handling either single or three phase. See, type 2 charger features. Safe connection and operation. As per it follows SAE standard. SAE is automotive standard. It follows SAE standard J1772. Power is extended only after connection to the electric vehicle. EVSC provides power only after connection to the vehicle. After this negotiation between EV and EVSC. How it is being done, that we will see in the upcoming slides. Earth missing detection, earth leakage detection. This already we have seen. Power load, short circuit protection, all those things we have seen. Pilot signal based status and maximum current available communication. See, pilot signal is nothing but a PWM signal based on the pulse width. The pulse width provides information on the maximum current available. And the amplitude of this pulse width modulation provides the status of the charging. See, this is the status. when the pilot pulse, that is the CP point, control pilot. The control pilot pulse, when the amplitude is plus 12 volts, it means whether plus 12 DC. When the amplitude is plus 12 DC, it means the EVSE is not connected. EVSE means electric vehicle supply equipment. Electric vehicles, when EVSE is not connected to the vehicle, you have a constant DC of 12 volts. When it is connected to EV, when it is plugged to the EV, the amplitude on the positive side becomes 9 volts, whereas negative is minus 12 volts. And the frequency of that pulse PWM is 1 kilohertz. So the EV has the effective resistance of 2.74K. This resistor is present in the EV. So when and a resistor of 1K is connected to the EVSE. From this 12 volt signal, a 1K is connected, and that 1K is now connected in series to this resistor 2.74K, and the other end is grounded. So when the voltage, if you measure the voltage across this, the voltage is the voltage what you get is around 9 volt. 1K in series with 2.74K, and the voltage across 2.74K is 9 volt. And there is a diode also in between, 1K and a diode. So what happens then? Minus 12 volt is not will not get divided. Only a positive voltage is will get divided. So okay, when the vehicle is ready for charging, or when it is charging, see, when it is connected, it is called state B. When it is not connected, it is called state A. And then when the vehicle is ready for charging, or when it is charging, it is called state C. During charging, the amplitude becomes 6 volt. That is because the electric vehicle connects a 882 ohms to that 1K resistor of the EVSE. So when it connects 882 ohm, you get around 6 volts across this resistor. Slightly less than 6 volt, because you have 1K and 882 ohms. So here the voltage will be slightly less than 6 volt. So when it is 6 and less, it is assumed as state C. State C is charging condition, and another one is state D. That is when the vehicle is charging and it requires cooling. A vent is required. It requires, when the vehicle requires cooling, the voltage becomes 3 volts. So that means the battery needs cooling. So some action should be taken either by the charger or by the vehicle to protect itself, protect the battery. When the amplitude is 0 volt, this is an error. Similarly, when the frequency is not 1 kilohertz, that's also an unknown condition. Okay. Now, based on the pulse width, you can see when the duty ratio, when the other duty ratio is nothing but ratio of on period to the period. So when that is 10%, it indicates current available from the charger is 6 amps. When it is 25%, it indicates 15 amps. So something like this. So when it is 96%, it means 80 amps. How that is calculated is given here. Between 6 and 51 amps, the calculation is different, while between 51 and 80 amps, the calculation is different. Again, it got stuck. See, this is how the control pilot signal looks like. See, this is state A. You can find a DC voltage of 12 volts. When it is connected to the vehicle, the voltage drops from 8 to 9 volts. This is state B. When it becomes 9 volt, it starts oscillating at a frequency of 1 kilohertz. You find a square pulse of, a PWM of 1 kilohertz. And this is connected and not charging. This is charging. 6 volt. It is charging. When the voltage falls further below, also it is charging when required. That is state D. Again, the connector, charging stop. So it becomes 9 volt. Unplug. It becomes 12 volt. And you can find the different duty cycle and the current values given on the right hand side. See, this PWM signal you find on the CP pin, a yellow color marked pin on the connector, that is control pilot pin. The control pilot provides this PWM pulse modulation. Okay, proximity. What proximity pilot does? It also provides information about the vehicle with the connection status. So here also, the handle, when you press, the connector has got a handle. When you press, see, when it is not connected, you get 4.5 volts at this point. When the button is pressed, when you press the button, you get 3 volts. When it is connected, you get 1.5 volts. See, this is the button. You can see the button here. This is the button. When you press the button, it gets open. So you get 3 volts. When the button is released, this is shorted and you get 1.5 volts. When it is not connected, see, this is right side is vehicle, left side is the charger side. So when it is not connected, this resistor doesn't come into picture. So you have 4.5 volts here. And the resistors used, values are given here on the top. This is type 2 charger. This RRT is supplying this type 2 charger to Mahindra electric vehicles. Mahindra vehicle, this E-Verito. For E-Verito, for European, for export applications, this charger we supplied to Mahindra Electric. And this charger goes with each and every vehicle. Similarly, we are supplying type 1 chargers for Tata Tigor. And this charger goes with each and every vehicle, with each and every new electric vehicle. Okay. This what we have seen so far is about AC chargers. So let us see what DC chargers consist of. What are the requirements for DC charging? See, this is it's a block diagram of a general block diagram of a DC charger. So generally, DC charger works on a 3-phase input, because the power requirement for DC charger or onboard charging is high. It has to charge the vehicle within hours duration. So it receives input from a 3-phase line. You have a circuit breaker, generally a MCB is molded case, molded circuit breaker. MCCB, molded case circuit breaker. Either MCB or MCCB being used for this application. MCB has got a magnetic tripping as well as thermal tripping. Similarly, MCCB also has got magnetic as well as thermal tripping. Whereas for higher current application, MCCB is used. For lower current application up to maybe some 63 amps, MCBs are being used. MCBs are cheaper compared to MCCBs. So you have at the input, generally there will be a power factor correction converter, active power factor correction converter. See, it doesn't have a single converter, and generally has two converter. One is active power factor correction converter, or also called as front end converter, which is used to provide high input power factor as well as draws a sinusoidal input current, so that the harmonics, current harmonics drawn from the mains is limited to less than 5%. So when you use a active power factor correction converter on the front end or a front end converter, it provides a good power factor, that is a high power factor that is close to unity, and it also provides low harmonic distortion, current harmonic distortion from the current drawn from the mains. So it maintains a sinusoidal current from the mains. Then this front end converter is followed by a DC-DC converter or an inverter, generally an inverter with isolation, with a transformer, isolating transformer and a rectifier. This inverter, isolating transformer and rectifier forms a DC-DC converter. And generally this voltage of the active power factor correction converter for a three-phase application will be somewhere around 800 volts. And from 800 volts, it is stepped down using this inverter, isolation transformer and rectifier. So the voltage is converted from this 800 volt to the required output voltage, generally 50 to 500 volts DC. See, normally the electric cars, four-wheelers, use up to 500 batteries of about 400, 450 volts, whereas large buses, they use 750 volt system, 750 volt battery system, and some trucks, they use 1000 volt system. So today chargers are available for charging four-wheelers that are capable of charging up to 500 volts, buses for up to 750 volts, and trucks for up to 1000 volts. See, this is my measurement, ammeter and voltmeter measurement, and there may be a diode at the output, so that multiple charges can be parallel. See, this is you see, multiple modules. There can be multiple modules within a charger. Maybe like say today maximum capacity of module available is about 30 kilowatt. So SMPS of 30 kilowatt is available as a module, single module. So when you require about 50 kilowatt, you can parallel two modules, so that you get around 60 kilowatt. When the requirement is about 120 kilowatt, normally for buses it requires 120 kilowatt. When you want to use it for buses, parallel 4 modules to get 120 kilowatt. And even up to 350 kilowatt requirement is also there for large trucks. And up to 10, 11 converters can be parallel to get that power value, power rating. And at the output of the charger, on the vehicle side, see normally on the charger side also there will be a relay or a contactor, as well as there will be a vehicle side relay also. So generally the charger will be connected initially without closing that output side contactor. When everything is okay, that contactor will be closed. Vehicle checks for normal function. When the function is normal and when it is safe, the vehicle also close the relay. Only then charging takes place. So if there is a mismatch between the charger and the vehicle, both the sides relays will not engage and charging will not happen. So that the safety of the vehicle is always kept as a higher priority. Okay, and this is auxiliary power supply. See, we need auxiliary power supply to to control all these things. Say we need a auxiliary power supply for the controller card, for the driver, all those things. So for that, we need auxiliary power supply, and also you need a communication. See, vehicle and charger generally communicates, and then depending upon the request from the vehicle, the charger provides the necessary voltage and current. So there is a vehicle to charger communication. In addition to that, there is a IoT, Internet of Things. That is, the chargers has got a chargers are all connected to the cloud, and the mobile applications are available to find out the location of the chargers, and the user has to authenticate himself before charging, and also payment also is made through the cloud connectivity. So all these things are done, and you need there is an energy meter also inside the charger, which measures the energy drawn from the mains. So the your rate for charging cost is determined from the energy consumed, maybe duration of the charging, etc. And accordingly, the server calculates the value, and it is indicated through the charger, and the payment can be done through some form of electronic mode. See, as I told you, the vehicle the charger doesn't act independently. It communicates with the vehicle, and then the charging happens. So for that communication, that should be a standard for that communication. So internationally, 3 protocols are being followed. One is the one initially introduced was CHAdeMO by Japanese. This is the oldest protocol available, and later came GB/T, the Chinese protocol, and European came with their own protocol called Combined Charging System, CCS. The Combined Charging System has got both DC and AC charging in the same plug, whereas CHAdeMO and GB/T, they have independent AC charging and DC charging. In fact, combined charging system plugs are expensive. Plugs and sockets are expensive because it combines both AC and DC charging in single plug. And in India, we have one more protocol called Bharat protocol. That is being used by vehicles like E2O, E-Verito of Mahindra, Tigor of Tata, etc. GB/T is mainly used in China. Chinese, this is the standard of China, and China, they use only GB/T within their country. And CHAdeMO being used by all Japanese vehicles, and vehicles sold other in European countries uses CCS protocol. Got stuck again. Okay. There's one more protocol, as I told you, that is Bharat charging protocol. The CHAdeMO Association. The CHAdeMO Association belongs to Japanese, and the main work of this CHAdeMO Association is to develop the protocol, certify the charge. They certify the chargers and promote the fast chargers. See, these are all history behind the CHAdeMO and their roadmap during so many years. They started the first R&D in 2005, and now, as of now, it is accepted. It is accepted as standard by IEC and EN. And now the CHAdeMO 3 version is capable of charging up to 900 kilowatt, and that's provision for two-wheeler charging also. So the charger's capacity, like for 500 volt charger, it can charge up to 400 amps, 900 kilowatt charger in CHAdeMO 3, etc. CHAdeMO not only uses the protocol for charging the vehicle, this protocol is available for different application. See, the vehicle is, it is only for, not just for charging the vehicle. The charged vehicle can be used to power the home. For that, V2H protocol is used. Vehicle to home protocol is used to power the home. So once say, for example, you charge the vehicle charge is full, and you can use the battery of the vehicle to power your home throughout the night. And you can charge the vehicle during maybe the lean hours, lean periods of the it's like see in the other countries, in India, we do not have that different charges at different time, whereas in other countries they have different rates for electricity at different time. So during the peak period, you can use it to power your home, and during the lean hours, you can charge the vehicle, so that you can earn, you can get returns from the vehicle itself. And you can use multiple vehicles, maybe some 20-30 vehicles in a flat and all. You can power a building itself using multiple vehicles. For that, V2B protocol is used. V2 grid, vehicle to grid. That is what, this is what I said. You can export power to the grid during peak hours and earn money. And during lean periods, you can charge the vehicle. Similarly, directly from vehicle, you can directly power a load. So that is also possible using V2L. So these are all protocols available from CHAdeMO. So this is CHAdeMO interface. See, this is a connector. This is a connector. You can see the CHAdeMO connector. I can show. See, you can see here, this is a connector or the plug. The plug has got 5 and 6 pin or power pins. They carry the DC voltage, DC positive and negative. And there are other 4 pins here and another 4 pins. They are all control pins. The control pins, what are the pins? That is shown here on the left-hand side. The left-hand side is the EVSE, electric vehicle supply equipment. Right-hand side is the electric vehicle. See, pin number 5 and 6 are being used for powering. 6 is positive, 5 is negative. Pin number 2 is used for charger start and stop. So when you press the D1, D1 is a push button. Like when you press a push button, when you make a contact here, it indicates the charger has started, and the vehicle understands it through this. When you press it, the power is extended to this optocoupler, and the output of the optocoupler is used to indicate the vehicle that the charger start button is pressed. When D2 is pressed, that is a stop button. It understand. No, this is not actually the push button. These are all relays. Relays are used. These relays are used initially when the charger is started. This button, this relay is operated. When the charger, when the other relay operates, charging is it is ready for charge. That is informed by G. So when you the connection, okay, when it is plugged, it is connected is determined by the H output. So when you connect it, the ground is extended here. See, ground is extended here on the charger side, while plus 12 is taken from the auxiliary battery of the vehicle, and ground for that is extended through the charger. So this optocoupler operates, and the status of H is used to determine whether the plug is plugged or not. Similarly, when these two relays are operated and everything is ready, a charge enabled signal is provided by the vehicle. Only when it see these two indicates that it is ready for charging. Only when the vehicle provides, when a vehicle will verify every parameter is okay and it is matching with the vehicle. Once if it is verified, it provides a go signal through K. Once the signal is on, the charger get to know through J, and the charging starts happening. This is the onboard auxiliary battery. Ground is extended to this. In addition, see, these are all digital signals used for charging. In addition to that, there is a serial communication through CAN bus. CAN bus is a two-wire bus. CAN high and low is there. This is a serial communication. It's a robust communication used in mainly in automobile and automation application. So continuously, there is a exchange of data between vehicle and the charger. The charger, say like charger provides, initially charger says, I am ready, I am available. It provides its own data. Then like it exchanges charger and vehicle exchanges the parameters like voltage, current, power available, and what is the power required by the vehicle, what is the maximum target voltage, and all being exchanged. Then the contactors of the charger is closed, the contactor of the vehicle is closed, the charging starts. When the charging starts, the vehicle starts to provide how much voltage required, what is the current required. So the charger follows what the vehicle requires. And when there is a difference in voltage or current, the charger, the vehicle stops the charging by disabling the charge enable disable. Okay, this is about the CHAdeMO. And that there is a sequence of charging also that we saw the charging connector details of CHAdeMO and the sequence of CHAdeMO charging. First is send start of charging signal. D1 is on. We have shown two relays, small relays. When D1 is on, it recognizes the start of charge. The vehicle recognizes start of charging. And the vehicle transmit battery parameters. Once we send the start of charging signal when D1 is on, you can refer to the previous slide for D1 and all. Here, see, this is D1. D1 and this is D2. Okay, and this is a charge enabled signal. Okay. So when D1 is on, the vehicle recognizes the start of charging and it starts transmitting the battery parameters like maximum voltage to stop charging, target voltage, total battery capacity, etc. That is received by the charger. Charger checks for compatibility. Once if it is compatible, it transmits the charger parameters. That is the maximum output voltage which it can deliver, maximum output current, and if there is any error, it shares the error flag. Vehicle again does the compatibility check and it calculates the maximum time to charge. Then it sends start permission signal. Okay. That is start permission is nothing but the K signal, that is charge enabled signal. The K, this one This one is K signal. That is sent once after exchanging the parameters. K signal is transmitted by the vehicle. Charger recognize the start permission and to J, and the connector gets locked. See, the connector has got lock and it gets locked to the vehicle, so that during charging you cannot remove the connector. So connector locks and perform insulation test. That is, it does the charger checks for the leakage in the charge cable. Not only the charger cable, it also checks for the vehicle side wire cables by applying a high voltage. Say a 500 volt charger applies about 500 volts across the positive and negative terminals. Verifies for the checks for a current, small current. Even if there is a small current, the insulation test will fail. If there is no current at all, the insulation test will pass. Then send charging ready signal. D2 goes on. Once the insulation test is over and the insulation test has passed, the second relay is turned on. So recognize charging ready signal. The EV contactor goes on. Now the vehicle checks for battery condition, temperature, etc., calculates the optimal charging current, and it transmits the charging current value every 100 millisecond time. And it checks for the current supplied by the charger. And if there is a difference, it provides error signal. The charger provides output current. So when the battery voltage reaches its required value, the time to terminate, the time comes to terminate the charging. So it sends a zero current signal. Once the battery is fully charged, the demand given by the vehicle becomes zero. So it demands only zero current. So output current also from the charger also falls down to zero. So now once the current becomes zero, the EV contactor goes off and sends charging stop signal. It removes that the charge enabled signal. Now the charger recognizes charging stop and it terminates the charging process, and the connector lock gets unlocked. So this is one charge cycle. So communication takes place right from the beginning, and during this period only here both digital as well as serial communication takes place. Here only serial communication takes place. Okay, this is an example of the serial communication. Like these are all the identifiers used by, see, this is the identifier used by, one shown in yellow is the identifier used by vehicle. The one shown in green is the identifier used by the charger. So this is the data length. Data length is 8 bytes. You can see 8 bytes of signal. So digital serial communication through CAN takes place between vehicle as well as charger. It uses, see, there are two types of identifiers. One is the standard identifier, and another one is see, the standard identifier has 11 bits, while extended identifier has 29 bits. This CHAdeMO protocol utilizes standard identifier, and number of frames used between vehicle and charger, they are minimal. Message interval is 100 milliseconds. In addition to this, there are other frames also being used, but the frequency is very low. That is used for like sharing the vehicle ID, then range related information, etc. This is RRT's charger. RRT has got CHAdeMO charger as well as GB/T chargers as well as Bharat charger. And these chargers were initially supplied to Mahindra Electric. These are all, this is 12 kilowatt charger, this is 15 kilowatt charger, this is 15 kilowatt charger. These chargers are used to charge e-Verito. Both Mahindra had a their exclusive protocol, and initially charger developed by us was used to charge the Mahindra protocol vehicles, and later they are all converted to Bharat protocol. So we have chargers, both Mahindra and Bharat protocol chargers available with us. So here you can see it has got both fast charging as well as AC slow charging. AC slow charging comes with the industrial plug, and fast charger comes with the GB/T connector. See, this is the latest RRT chargers, all SMPS based chargers, while the one what you saw is a conventional one with the DC-DC converter, which had a transformer rectifier unit plus DC-DC converter, while these are all switch mode power supply, has got active power factor correction circuit as well as a DC-DC converter built into it. We have 15 kilowatt single gun charging, 10 kilowatt single gun charging, then 20 kilowatt dual gun and 30 kilowatt dual gun chargers. See, as of now, the chargers available in the market, RRT chargers of the Bharat protocol chargers has got the smallest footprint. See, these are all the charging plugs. This is CHAdeMO plug, charging gun. The middle one, the left one is CHAdeMO charging gun. Middle one is GB/T charging gun, which is used for Bharat protocol charging also. The rightmost one is combined charging system gun. So both AC charging as well as DC charging is present in the same gun. We have seen GB/T, functioning of GB/T and the GB/T gun details also we have seen. Now, CHAdeMO gun details we have seen. Functioning and gun details of CHAdeMO we have already seen. GB/T gun, this is GB/T gun. See, this is almost similar to what is being used by CHAdeMO, except few modifications. You have DC, say the pin number 1 and 2 are DC connections. Here also we have two relays, D1 and D2, similar to what is being used in CHAdeMO. But the other side, on the EV side, it is slightly different. So this is for connection check. Connection check, when the ground is extended here through this resistor. So once this is connected, the vehicle understands the charger is connected. This is again start from charger. Start is understood by this optocoupler. Then when this D2 is switched on, it extends the charger status, contactor status to the vehicle. When it is switched on, the vehicle contactor is also switched on. Similarly, here also, CAN, it has got a serial communication through CAN protocol. What are all the messages transmitted in GB/T protocol? That we will see. Similar messages are used for Bharat protocol also, except for a small modification. There is a handshake messages, charger handshake and vehicle handshake. See, C represents charger, B represents battery. That means vehicle side. So CHM, charger handshake, BHM is vehicle handshake. CRM is charger recognition. Charger is recognized by this message, vehicle is recognized by this message. And see, this is the PGN number. This is actually this number. Once you try to learn about the CAN communication, you will understand what is PGN number and all. And the priority between messages, like when 2-3 messages comes at the same time, which message should be given priority? So that priority is given here. So the one with the highest priority will have the lowest number. The ID, the priority is added to the ID. So the ID number, which has the lowest value, has got the highest priority. And how much data length is used? So that is given here. So we have seen in ChatDemo 8 bytes of information for CAN communication, whereas here we see say up to like 41 bytes. So when we try to use more than 8 bytes of information, this is the transmission, and transmission is done through a separate protocol, so that it can accommodate more number of data bytes. And message period is 250 milliseconds, whereas in ChatDemo it is 100 milliseconds. Then after handshake and after recognition, charging parameters are exchanged. It's called BCP. BCP is from the vehicle battery. Charging parameter is exchanged from the vehicle to the charging parameter is transmitted from the vehicle to the charger. Then charger sends time synchronized information to the vehicle. Then charger shares the maximum output details. So here the parameter is exchanged between these two. Parameter is exchanged between vehicle and charger. Then battery charging demand, the current demand and voltage demand is provided by the vehicle through BCL message, and overall battery status is shared by the vehicle. So this BCS information can be used to find out the battery health condition. It can be used to study the battery health condition. Then charger status is provided by the charger. Then battery power storage battery status information is shared by the vehicle. And single power storage battery information is also exchanged by the vehicle. Which battery has got highest voltage or lowest voltage, those information and its identity is shared by the vehicle. Similarly, temperature, which cell has got the highest temperature, and what is the identity of the cell or identification number of the cell. Similarly, which cell has got the lowest temperature and its identification. These are all shared by the vehicle. This is reserved, and this is suspend charging. Once the voltage reaches, or once a cell is overcharged, the battery of the vehicle suspends charging. Based on that, the charger suspends the charging. It sends a suspending message, vehicle sends a suspending message, and charger suspends charging. Charger also can initiate stopping of charging based on its once the voltage is reached, it also can stop the charging process. Once after the charging process is completed, statistical data is exchanged, is provided by the battery. That is vehicle battery data is provided by the vehicle, and the charger data, like what was the current, how much time it taken to charge, all those information from what SOC to which SOC does charge, those information are shared by charger statistical data. And error messages, these error messages basically there's a timeout messages for each and every messages whatever we have seen, right from handshaking, charger recognition, parameter exchange, or demand, or battery status information. So everywhere when there is a timeout, that is indicated by this BM for vehicle and CM for charger message. So this is how the CAN identifier. The CAN identifier is formed using the priority bit. Priority bit is 3-bit, extended data page bit. All those information you will come to know only when you go through the CAN protocol. Then data page bit, PDU format, PDU specific, that is which this is the target. Specific is nothing but the target address. This is the source address, etc. Based on these things, the identifier is formed. Once you know the PGN number, you can from the PGN number you can find out PDU format, PDU specific, and source address and all, you know. So we can create a identifier, and the priority, once it is known, identifier can be created. See, this is a PGN. PGN has got, this is the format of a PGN. This is the data, external data page, DP. Once you know PGN, you can find out from this. Then PDO format 8 bits and PDO specific 8 bits. So this is a priority, as I told you. The priority, highest priority is 0 as the highest priority, and 7 is the lowest priority. See, other than the messages, there are some control messages are also there, and for that control messages, the priority is 3. And for all other informational proprietary request and acknowledge message, the priority is 6. Then we come to the European standard plug, CCS. So the one on the left side is a plug, and the one on the right side is a socket. You can see we have seen type 2 charger. The AC part, AC charging part is similar to the type 2 charger. Not similar, it is exactly same as the type 2 charger. So it has got L1, L2, L3 lines, neutral, power earth, control pilot, proximity pilot, etc. And in addition to that, we have two power pins, DC positive and negative. See, this is actually so far whatever we have seen, they are based on CAN communication. The vehicle charger communication was through CAN, whereas this one CCS is based on TCP/IP protocol, and it follows the OSI model. So you have the application layer messages at the top, and efficient XML interchange EXI. This is a coding. This is an encoding of the application messages, and vehicle to grid transfer protocol. Then, like in whatever there in TCP IP, you have UDP and TCP, TLS transport layer security layer. Then internet protocol. It has 7 layers. The physical layer is the first layer. Data link layer is the second layer. Then the network layer, transport layer, session layer, presentation layer, and the application layer. And the standard followed by each layer and all is provided here. This is how charging takes place here with CCS. See, there are two types of communication. One is high-level communication. That high-level communication takes place through power line communication. The TCP/IP communication takes place through power line, and there is a low-level communication that is done by the pilot. Low-level pilot signal, like what we have seen in Type 2 charger. See, normally, the Type 2 charger has 1 kilohertz signal, and the pulse width determines the current what it can supply. Whereas here, when the pulse width goes below, there we have seen pulse width started from 10%. Here, when the pulse width is less than or equal to 5%, it means the communication is through digital communication, through high-level communication. That is through power line communication. So, if it doesn't go below 5%, the high-level communication will not take place. So, the low-level pilot initially will have 100%, and once when the communication tries to start, it becomes 5%. Once it becomes 5%, it indicates that the high-level communication is going to take place. So what are all the sequence of communication, that and all we will see later. See here, as I told you, charger has got a relay or a contactor at the output of the power unit. Similarly, a disconnecting device or a relay or a contactor is available on the electric vehicle side also. So once everything is okay, the relay closes here in the DC power stage, I mean the charger side. Similarly, when the vehicle checks and finds everything is okay, it closes the contactor. When there is a mismatch, vehicle itself trips by disconnecting the contactor. So charging sequence. Yeah, this is similar to Type 2 charging. Connection status through 1 kilohertz speed volume signal. The amplitude is again checked whether it is connected at all. When it goes to 9 volt, it is connected, and when it goes to below 5% or equal to 5%, it means high level signal. 1 kilohertz speed volume signal generated by CP. High level communication for charging, TCP/IP based. The link is established by power line communication using home plug green pi physical layer. The physical layer used is called home plug green pi physical layer. It's a special physical layer device used by electric vehicle charging. Charge process sequence starts with 5% PWM signal at 1 kilohertz to trigger the HLS. This PLC is generated by this PLC communication is done by a special chip from Qualcomm. PWM states, like already we have seen, state A, B, C, all those things we have seen. Same is applicable here. Once state C is attained, EV proceeds to establish high-level communication. High-level communication is high frequency signal and may skip the limits of private electrical network, resulting into a crosstalk. High-level communication is, as I told you, it's a power line communication. It is like RF communication, so it may skip the limits of the private electrical network. So to establish that only correct EV and EVSC join a common network, a signal attenuation characterization protocol is used. SLAC is used to ensure only that right EVSC and EV communicates. It should not communicate with a different EV. Being RF signal, it should not communicate with a different EV. So the SLAC, signal level attenuation characterization protocol, is used. That means EV sends sounding packets as broadcasts to all charging stations on the same electric. So what happens? EV sends the sounding packet, the one with lowest attenuation. The charger with lowest attenuation determines that one is connected to the, or the EV determines the charger with the lowest attenuation is the one that is connected to its network. SLAC measures the one which is close to that or connected to that will have the lowest attenuation. The others attenuation will be more. So SLAC measures the attenuation between PLC modules that exhibit lowest attenuation to each other is physically connected. Once that is ensured, EVCC, that means electric vehicle charge controller. EVCC means electric vehicle charge controller, uses SCCC, supply equipment. Supply equipment is charger. Supply equipment charge controller. Supply SCCC discovery protocol to obtain the IP address and part number of port number of SCCC. The discovery protocol, that is, electric vehicle discovers the supply equipment. So that's why it's called discovery protocol. So discovery protocol and obtain its IP address and port number from this. TCP/IP version 6 is set up. The communication sequence starts with the following application layer messages. It's getting stuck. Okay, this is a charge sequence. The first one is supported application protocol, request and response. Request and response are the protocol compatibility. There are two specifications, two standards are used. One is DIN standard. DIN standard is called CCS 1.0 and ISO 15118 is called CCS 2.0. Some older vehicles use CCS 1, that is DIN standard, and latest vehicles use CCS 2, that is ISO standard. So this So the protocol is discovered. Which protocol is used is discovered through the supported app protocol, the request and response exchange. Then a session is set up. The charging session is set up, establish a communication session and exchanges client server IDs. Service discovery request and response. See what service is required. That is discovered using this communication. See, like it can be a charging service, or it can be a certificate enabling, embedding service, or it can be a power export service, something like that. See, it doesn't do only charging service. So you can embed a certificate, like authentication certificate can be embedded into the vehicle, or a certificate with the mobility operator for charging to up to this amount, something like that, like a prepaid card, something like that can be embedded, electronically embedded into the vehicle, so that the charging doesn't require authentication or payment. So it all being done automatically. A hassle-free charging happens. Just go plug the charger. It doesn't ask for anything. It charges. Once it is charged, remove the plug and can drive the car. So that is called plug and charge. So without any hassle, it's a hassle-free charging. So you need an electronic certificate from your mobility operator embedded within your vehicle, which provides both authorization as well as payment. So using that one, you can have a hassle-free charging. So the service requirement you have to provide. Either you want to export the power from the vehicle to the grid, or you want to charge your vehicle, or you want to embed a certificate, electronic certificate. All those things can be provided in the service discovery request communication. Then service payment selection. What type of payment you want to make? Whether it is automatic or it is through POS or something like that. Those information. It can be an external payment or internal payment, like with a certificate, that you can select. Contract authentication. So initially there will be authentication. That authentication has to happen through either through external means or through a certificate. External means mostly consists of RFID. RFID authentication, or it can be through a certificate, can happen. Then charge parameter discovery. So both vehicle and the charger exchanges the charge parameters, and if they find it compatible, it can proceed for further charging. Once the parameter is exchanged, when it is compatible, it goes for cable check. That is isolation checking, insulation verification. It checks for cable insulation by applying a high voltage, verifies the cable up to the car's relay, the vehicle's relay point. So up to that, the insulation is verified by applying a higher voltage and checks for a small current. If there is a current, insulation fails, insulation test will fail, and if there is no current, insulation test will pass. Then pre-charge. Pre-charge is nothing but initially the charger voltage matches with the vehicle battery voltage. So before the relay on the vehicle side closes, both the voltages are at the same level. That is, the charger voltage raises to the battery voltage and remains there, so that when the relay is closed, there will be no current flow on either side. Both voltage will be on the same level, and when it closes, there will be no current through the contactor. Then charge current demand, power delivery request. So now the vehicle will provide the current demand or the power demand, so that power delivery, and when current demand also it will provide. Based on that, the charger will provide required current. So once charging is completed, the charger checks for welding detection. That is, whether the contactor is welded or the relay is welded. Before, while it is opening, it checks whether it is welded. If it is welded, the charger further will not work, and it will till it is rectified, it will not provide the service. So it is for welding detection, because high current is flowing and this is a DC charger. When the relay or contactor opens, there will be arc, and these relays has arc protection, arc suppression methods, which suppress the arc so that welding doesn't happen. But in case if it happens, the charger will isolate itself from the charging process till it gets repaired. Then comes a session stop. Once everything is over and everything is okay, then the session stop request is there, or the session comes to an end, and the session is closed. So this is one cycle of charging. Okay. So I hope this would have given an initial idea of about what the electric vehicle charging is, what are the protocols being used, how the charging happens. So all this information you would have got from this session, and hope this will be of some use to you. And DC charger are highly complicated, but whereas AC chargers, even the students can themselves develop AC chargers. The one which we shown initially, like without IoT. That is a very simple one. You can develop as your college project itself. Whereas one with IoT and energy measurement, slightly complicated, still it can be done by the student itself. So you can try this for your upcoming project, and hope this will give an introduction. This would have given a good introduction for you regarding electric charging. Thank you. And if there's any question, you can raise it now.
If you have any question?
Good evening, sir.
Good evening.
Sir, in that charge plug, you told that on PP, PE, CP, and something is there.
Yes.
Full form can I know, sir? Actually, I am based on electrical. I am an electronic student. So,
The CP is control pilot.
yeah.
And PP is proximity pilot.
And PC is PP.
PP is proximity pilot. PP is proximity pilot. Hello.
E, sir.
P is power earth.
Power earth. Okay.
Yeah. P is power earth. CP is control pilot. CP is mainly used to communicate between vehicle and the charger.
Okay.
It provides information on how much current it can supply, as well as the connection status. While PP provides only connection status.
Okay. Thank you.
Now, generally, PP is rarely used.
Okay.
So most of the information we get from CP itself.
In that next slide, the charging after 12 volt, you told that after load is given, it is decreasing around 9 volt.
Yeah.
But if you are going to see the cycle, just pulse cycle, The top one is reduced 9 volt, but bottom one is same minus.
Yeah,
3
yeah.
is there, sir.
Yeah, bottom. See, actually, a diode is used in series on the vehicle side. So, what happens? Only positive voltage reduces. Negative voltage doesn't reduce.
Okay. Only positive.
Yeah, negative should maintain at minus 12 volt.
Okay. Thank you, sir.
Okay,
Thank you, sir. Nice question.
welcome. Anyone else?
Please raise your questions. If you have any doubt, you can raise your questions now. It is a discussion session.
Need not bother even the question is silly. Since it's only the first time you are hearing about these things. So don't bother about whether you are asking a right question or not. Anything, even if it is a silly question, no issues.
Sir, there is a question by Venkatesan G. Whether
Okay.
charges vary from place to place.
Charging?
Whether charges vary from place to place.
Yeah, correct. It varies from place to place. Like as I told you, we have different type of protocols. For say like European follows CCS, while Japanese follow CHAdeMO, China follows GB/T, and some Indian vehicles follow Bharat protocol. So depending upon the country you visit, charger there is a there is a variation in the charger protocol being used, and you cannot use a GB/T charger for a CCS vehicle. Similarly, CHAdeMO vehicle cannot be charged using a CCS charger, and the chargers themselves have some chargers have up to 3 guns, different guns, so that they can charge either CHAdeMO or CCS or GB/T. And there are many chargers that has both CCS and CHAdeMO. See, GB/T is only followed in China. So other than China, both Japanese vehicle and European vehicles are there, and many chargers have 2 guns. Also, voltage levels varies. There is no standard. There is no standard single charger which can charge all the vehicles. Generally, 4-wheelers are limited to, say, Indian 4-wheelers. The chargers, Indian vehicles like Tigor or E-Verito or E2O, they work from either 48 or 72 volt system, battery system. The current rating is high. They draw up to 200 amps. Whereas high voltage system, high voltage battery system, they operate at say somewhere around 380, 400 volts, but the current requirement is less than 100 amps or 125 amps maximum. Similarly, for higher buses and trucks, the voltages are slightly higher, 750 volt and 1000 volts, but current is limited to maximum of 125 amps. So charger differs from place to place. Yes, it differs. And at many places, many malls and theaters, you find AC chargers, which generally takes hours together to charge a battery to full value. But it can be used to top up the vehicle. And many workplaces, AC chargers are available. That can be plugged in for about 8 hours or 9 hours during the working hours, so that you by the evening when you try to return, the vehicle gets almost fully charged. But DC chargers are quite big, takes less than an hour for a full charge. Different nomenclatures being used, as I told you, rapid charging, quick charging. There's one thing called flash charging also. See, normally public transport like bus, they do not want to overload the bus with high capacity battery. So battery will have a minimal capacity, and initially it will be charged with a fast charger to its full value, full range, and full range may not be very high. It may be only hardly 50 kilometers, but one trip may cover about 100 kilometers. So 50 kilometers is not sufficient for it to complete one trip. So what happens at every stop? It stops for about 1 minute, and there is a flash charging. Normally, like pantograph like charging, the chargers are there, where there will be a pantograph that will come down and get connected to the bus, and it provides high current charging for a small.
Sir, it is not audible.